Hey everyone, we're going to be talking about one type of integral of a function. So we're going to start with a really simple example because it totally will make a point. Say you have the most boring road trip ever. You drive exactly 60 miles an hour for 5 hours. Not that you could do that, but hey, we'll pretend. So if you did that, you would obviously go 300 miles, right? Because we know from like middle school, distance equals rate times time. So our distance is that 60 miles per hour times 5 hours. I'm writing my units there to make another point. So we know that's 300 miles. We know that just intuitively, right? But look at our units, miles per hour and hours. Oh wait, miles per hour times hour? Wouldn't those hours just cancel, leaving you those miles? Oh, we might be onto something there. Now look at what the graph of this is. If you have 60 miles an hour shown on that horizontal line, look at this guy right here, this rectangle. It is 5, now bear with me on this. We could say that this rectangle is 5 hours wide and 60 miles per hour tall. So the area of this guy is that same 60 miles per hour times our 5 hours, and that's the 300 miles. So this area that's between our function, which is a really boring horizontal line, and the x-axis, that is what's called a definite integral. And it's super boring in the case of something like this horizontal line. And it's also not the reality. The reality is that if you were driving for 5 hours, your velocities, your speeds, might look more like this. Like you're driving along, you get slower, you get faster, you go, oh crap, I'm speeding, and then you hit a traffic jam, that's what happens. So, will the same logic work? Like, will this area give us our distance? And it totally will. Because if we look at just a single one of these little squares, it's 20 miles per hour tall and 1 hour wide. So the area of one square is equal to 20 miles. So if we can find the area that is between our function and the x-axis, that area will also give us our distance. And that area is called, once again, a definite integral. So we have to figure out how many squares we have. And we can go through and we can just count up all the whole squares. So I'm actually just gonna kind of block them all off. So I'm gonna call this a whole square. I know it's a hair short, but I'm gonna say close enough. And then so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 whole squares. Now we need to find the portions of squares. And so if we look at individual parts of squares, we can figure out our areas for them by just simply estimating. And we don't want to estimate more than like 0.1, by any more accurate than by 1/10 of a square. So looking at this guy, this little first region right there, I would call that maybe 0.6. This next piece right here, that's kind of almost a trapezoid sort of shape, I'm going to call that 0.8. Now you might look at that and say it's 0.7. Well, that's cool too, close enough. And then here, I'm going to call this a half, 0.5. Down here, this little lump, I'll call that another 0.8. And then I'm going to combine this little extra bit in with this below, because it's like those can kind of combine, the out and in bit. It's an estimate. That's cool. And then finally, this last little piece is 0.2. Why not? So we have our 10 squares plus our 0.6 plus our 0.8 plus our 0.5 plus the 0.2 plus the 0.8 plus the 1. And I wouldn't expect you to write all that out necessarily, but that's fine. So our total area is, let's see, here's 1, 2, 3.4, 3.9. Did I count right? 13.9? I don't know if I counted right. Let's say I did. Oh, please say I did. So we have, but that's squares, right? So each square, though, we had said is 20 miles per hour tall. I'm going to change my units the way I'm writing that. Oh, sorry, I just totally shook the camera. 20 miles per hour times 1 hour, because the width is 1 hour. So that's 20 miles. So our distance then, we counted up our squares, and then we went, wait a second, each square is 20 miles. So our distance is 13.9 times the 20 miles for 278 miles. Now, we're going to be using like velocities and distances a lot right now, but obviously this applies to a lot of other areas. But I'm not going to get into that. But there's some things that we can always know about these definite integrals. Namely, a definite integral is the area that's between a function and the x-axis. It can actually be positive or negative, which is a little weird. We find our units by multiplying our x units times our y units. And then I drew a little picture to show like a negative value for an integral would be if you're below the x-axis. Because if you think about it, you have like negative y values. And so if you have a negative y times a positive x, that's a negative. So that is our introduction to definite integrals. And it just as a thought to leave you with, there is a second type of integral. If one type is a definite integral, do you have any guesses about what the other type of integral is called? Maybe, maybe not.